In process control classes, we'll commonly use these terms transfer functions, and we'll throw them about, and we work in the frequency domain, and all you see is S's. And if you don't know what's really going on, it's really hard to follow. And if you're like me, I get lost pretty easily when I can't follow. So what I'm going to do in this video is go over how, if you're a process control engineer in practice and you need to determine what the transfer function is of some kind of system that you're working with, how do you actually go about doing it? And so the first thing we're going to do, or one of the things we can do, is perturb our system. And it's very common. We'll use unit step inputs as means by which we can derive how our system will respond due to some kind of change. And if we look at the graph to the left here, y of t can be a variable like temperature, for instance, and our input could be some kind of heater duty. And what we see is when we increase our heater duty by 10 kilojoules, the temperature of our system will rise gradually and then taper off to a new temperature, a new steady state value. And it takes a certain amount of time for this to happen. So there is a process time constant tau p that we need to find, as well as a gain, which is kind of a response. It's how susceptible our output is to changes in our inputs. And so if you are an engineer and you can see, if you observe this behavior from your process, how do you go about finding what G of P is? And so the first thing to note here is that we're at 0 at T initially. So this axis here, Y is a deviation variable, meaning that it is the deviation from its initial steady state value. And so in this case, we can see, like, if we increased our heater duty, our temperature deviated 2 degrees higher from its initial value, is what this is telling us on the y-axis, and it reaches this value after 5 minutes. And so this 2 tells us, if we go back to the definition of K for a unit step input tells us delta Y over delta U. Because it's a unit step input, delta U is equal to 1, and we just found that our delta Y had to be 2. So we now know that our gain in this situation is plus 2. Now the next thing to ask ourselves is, because the unit step response was applied at t equals 0, there was this delay for 2 seconds. And in the frequency domain, the way we represent these delays is with exponentials. So we're going to introduce this parameter called theta, and we're going to call it 2 because we see this no response until 2 seconds later on after we've increased the heater duty. And finally, we need to get our tau p value, the characteristic time constant of our system. And so if we go 63% of our gain, so 63% of 2 is 1.26. If we look at the time it occurs at, which is 5, we can see that our time constant will be 5 minus 2, which is equal to 3. And if this had units of minutes, our time constant for our system would be 3 minutes. And now that we have derived what tau p and k are, as well as realized what our lag is, we will look at what the definition, or we will look at our kinds of transfer functions we have in our toolbox. And because we're not seeing any oscillations in our system, and by that I mean we're not seeing something kind of go up and then taper off or start doing this kind of oscillatory behavior, because we do not observe that, and also we have a maximum slope at t equals 0, this indicates we have a first order process, in which case we know that GP is equal to some gain kp divided by a time constant tau p times s plus 1. And in addition to that, because we had a delay because our input happened 2 seconds, or our output responded 2 seconds after we changed our input, we include this exponential term minus theta s, and this is where we can now plug in our values for our system that we've observed. And ultimately what we arrive at is that our process here has values of Kp, which is 2, over tau p, which we determined was 3, times s plus 1. And we're going to multiply this by the exponential minus 2s. And so this is the process transfer function of our system. The process transfer function is a physical characteristic of our system. We cannot change it as a process control engineer. But what we can do now that we have GP is realize that GP tells us, maps the response of an output to an input U, and this is in the frequency domain. Now we can move forward and go about determining how our process would respond to other types of inputs, because in this we had a unit step input, but how would our system respond if we had an impulse input or some other kind of perturbation in our system? And so now that we've arrived at GP, I'll go over how we can determine what we can do later. And so I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.